Howdy, y'all! I'm Rissy, molecular biologist and skincare-loving weirdo. In celebration of this time of spring cleaning, today we're going to talk about the science of how we cleanse our skin. So, anybody ever notice that when we talk about cleansing our skin, we generally don't say, I clean my skin. Is it because it makes it sound too much like your skin is a rug or something? I don't know. It's that time of year in the Northern Hemisphere where the flowers are budding, the birdies are chirping, and it's time to purge the filth from ourselves. This is going to be a two-part video series. In part one, we're going to discuss the science. Why it's actually harder than you think to give your skin the cleansing it really needs, and the triumph of human ingenuity on a molecular level. In part two, we'll talk about how humans have been applying this chemistry for thousands of years, and all the different types of cleansing products that have since emerged, and how understanding all of this can help you make more informed decisions about what kind of cleanser is right for your skin. So to kick it off, the chemistry is actually pretty simple. All we have to discuss is water and quantum electrodynamics. Don't run away, I swear, it's really not bad. Let's rewind a bit. Let's start with water. Water is a molecule most fabulous. It plus the sun are why we have life on Earth in the first place. In chemistry, water is called the universal solvent because you can get so many different things to dissolve in it. But one thing that does not dissolve in water is oil. You've probably heard the saying, oil and water don't mix. And if you need to test the veracity of that, well, all you have to do is go to your kitchen, get some canola oil or olive oil, pour it in a glass with water, and notice how they settle out to be two different layers. Now, when we think about getting our skin clean, it's always the idea of washing with water. But paradoxically, water is actually not that good at cleaning your skin. What am I talking about? Well, if you haven't already watched it, I highly recommend that you go and watch my video on just the basics of human skin, which I will link up in the card and down below. But to make a long story short, the dirt that accumulates on our faces isn't actually like dirt, unless you've been rolling around in the fields or something along those lines, in which case, if you're literally encrusted with filth, then yeah, just a simple washcloth and some water can do you a lot of good, but that's not really what we're talking about. What we're talking about is just the kind of regular accumulation of oily grime that gets on our faces every day. And how does that happen? The natural oils that our skin produces over the course of a day pick up a lot of particulate matter that's in the air. Dust, car exhaust, that kind of stuff. There's also makeup. Human beings have been using makeup in some form pretty much since we developed tool usage, and most forms of makeup are composed of oils, fats, greases, that sort of thing, or they're made out of powders that mix with the natural oils on your skin over time, which is one of the reasons why your makeup tends to break down over the course of the day. All of that kind of mixes together in a sort of grimy sludge. The more polluted the area you live in, the worse it gets. What you're trying to get rid of on your skin is that day's accumulation of dirt. Doesn't sound right to me. Dirt is dry. Should we call it grime? Should we call it filth? We come from filth. We're going to filth. We're filth. We're filth. Timely reference. Anyway, it is important to get that stuff off of you. All that particulate matter in a modern industrial society, a lot of that is gonna be pollutants that can really damage your skin if left on there for too long. Water on its own can't fix that problem. But why is that? Why don't oil and water mix? Well, this is the part we get into about quantum electrodynamics, and again, I swear it's not actually that complicated. So to get down to real basics, I'm sure you know about atoms. And what is an atom? Well, an atom is the smallest bit of one of the elements that still retains the identity of that element. I'm sure you've seen the periodic table before, and these are the basic elements that make up our universe. But what determines an atom's identity? What makes something helium instead of hydrogen? That's the number of protons an atom has. And the protons are how we get the number of the element, so hydrogen literally just has one proton. That's it. For every proton in the nucleus, that's the center of the atom, you have a corresponding electron. And the electrons live in this kind of cloud around the atom. You may have seen like shells and things like that, Bohr models. So boring. Niels Bohr has been dead for a hot minute. He can't do anything to stop me. Ha ha. But the truth is, those are just models that help us understand atoms better. It's more accurate to conceptualize the electrons in the atom is moving around this cloud. It's also important to remember that opposites attract. And what am I talking about? Protons are positively charged and electrons are negatively charged. Positive and negative charges are attracted to each other, and that applies to molecules as much as it does to protons and electrons. So we've got atoms, they have a nucleus that's composed of protons, which gives that atom its identity. So the difference between hydrogen and helium is, well, hydrogen has 1 proton and 1 electron. Helium has got 2 protons and 2 electrons. There's also things in the nucleus called neutrons, but they don't really come into play here. We're not gonna fuck with that shit. So while it's the protons that give the atom its identity, it's the electrons that determine what it can do. And by what it can do, I mean, how does it interact with other atoms? What kind of chemical reactions is that atom capable of entering into? Here's where things get a little complicated. Certain elements are more electronegative than others. What does electronegativity mean? Atoms are a lot like different types of people. Some people have a really hearty appetite. They're just always out to eat everything they see. That's food. I'm not talking about cannibalism. And then there are people that just don't get all that hungry. For whatever reason, they don't have as strong of an appetite. Well, that's kind of what electronegativity is. Electronegativity indicates how much any given atom of an element wants electrons. To what degree does it attract electrons to itself? What on earth does any of this have to do with how to clean your skin? Well, as it turns out, water, of course, has 1 oxygen atom and 2 hydrogen atoms. And the interactions between the electrons of these elements is why water has the properties that it does. Oxygen is an extremely electronegative element. It is a big, fat, greedy hog. It just wants all the electrons for itself all of the time. Oxygen is like the cookie monster of electrons. Nom, 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 nom. Nom, 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 nom. Whereas hydrogen isn't really all that electronegative, meaning it's more electropositive, willing to give up its electrons to another atom when they are bonded together. The electronegativity of an atom determines whether the electrons in a bond are equally or unequally shared between all of the atoms. So with water, you have super electronegative oxygen, and then you have electropositive hydrogen. So what happens in the bonds that are holding these atoms together to form the water molecule is that oxygen is kind of sucking up all the electrons in those bonds, and it means that part of the molecule, and I'm just gonna put on this symbol, has a slight negative charge, which in turn means that those 2 hydrogens each have a slight positive charge. There's an electronegative and 2 electropositive poles. Just like the poles on the Earth, we have the North and the South Pole. Well, here we have the electronegative and the electropositive poles. Slight negative charge, slight positive charge. Since it's got this pole, the water molecule is polar. You've probably heard this before of people saying that water is a polar molecule, and now you know what that really means. Water is also a bent molecule. The oxygen and the 2 hydrogen atoms are always held at the same angle. This gives the molecule a front and a back, a north and a south pole, however you want to think of it. And keeping those parts of the molecule distinct in terms of their charge is part of how water is able to do what it does. On one hand, that's what makes it so good at having things like salts dissolve into it, because a salt is generally composed of positively charged atoms and negatively charged atoms held together by those opposing forces, because opposites attract in chemistry. If you dissolve salt, sodium and chloride, in a glass of water, what's actually happening is the water molecules go in and the oxygen is attracted to that positive sodium, and the hydrogen parts of the molecule are attracted to that negatively charged chloride. Sodium, by the way, is really electropositive. It's like, ew, I don't want your electrons. Gross. The water is able to just go in and bust that shit up. All of the atoms fly apart and are carried away by the water, thus it dissolves. What does that have to do with cleaning our faces? Most of the grime and filth that accumulates on our skin is non-polar molecules. Long chains of carbon atoms bonded to each other and then to hydrogen atoms. These are called hydrocarbons, and hydrocarbons are generally non-polar. Why is that? Well, there's very, very little difference between carbon and hydrogen in terms of how electronegative they are. They're just not really hungry for electrons, so the electrons are shared evenly throughout their bonds, which means those molecules don't have a pole. There's no partial positive or partial negative charges in hydrocarbons. And since like dissolves like, and on one hand you've got water, which is polar, and then a bunch of non-polar hydrocarbons, you see how trying to wash your face with water alone is really just smearing the greasy filth around. The oil can't dissolve in water because it is non-polar. What do we do about that? How do we actually get rid of the the dirt and grime on our skin. It's not good to let it sit there. In order to properly remove this stuff, then we need a special type of substance composed of special types of molecules. Molecules that manage to be both attracted to water, which is polar, and to hydrocarbons and greases, oils, and fats, which are very non-polar. Well, how do you split that difference? What would our special molecule look like? You'd want something that's both polar and non-polar at the same time. How are you gonna do that? Maybe a molecule that has two parts to it. Part of it's polar and part of it is non-polar. Can you do that in one molecule though? As it turns out, yes, you can. A special type of molecule that's part polar and part non-polar is literally the definition of soap. And we've been making soap for about 5,000 years. Soap, in pretty much every form, whether you're talking about soap or more modern synthetic detergents, and we'll get to all of that in part 2, don't worry. But the point of these cleansing substances is that they are made of molecules that literally have a polar head, a really electropositive atom bonded to a really electronegative atom, creating that polar head of the molecule, and then it has a long tail that's just composed of what? Hydrocarbons! The polar head of the molecule can interact with water, meaning that it is hydrophilic, it is water-loving because of its polar nature, and then the tail is attracted to hydrocarbons, to grease, and to oils. Thus, it is hydrophobic, meaning it pushes water away. This combination of properties, being partially hydrophilic or polar, and partially hydrophobic or nonpolar, makes a molecule amphipathic, i.e. extra special. And that's what soap is. Soap is made of amphipathic molecules. So you put it onto your face, and immediately it starts breaking down the grime by making what are called micelles. Side note, to me that always sounded like something a pirate biologist would say, "Arr, micelles!" So you put this on your face, and it immediately starts breaking down the dirt and grime because those long non-polar tails are attracted to the greasy dirt and surround it, making the micelle, with the polar head on the outside of the micelle, which means that the polar head is free to interact with water. So the water can carry away those micelles, each one containing some grease and dirt. Soap literally makes oil and water mix by trapping the greasy dirt particles inside of micelles. And that is how we wash our skin. It requires something that allows you to suck up all the grease and the dirt into these little particles that can then be washed away by water. And there you have it, my friends. Not that complicated. At some point in our history, humans figured out exactly how to make the type of substance that allows not just for the breakdown of oil and grime, dirt, and filth, but also how to carry it away. But isn't soap actually bad for your skin? Isn't it like drying and stripping and takes away all of your natural oils, that it's basically too good at its job? And what about all of these evil modern chemical detergents like sodium lauryl sulfate? How do we actually apply these principles of chemistry to the filth of our everyday lives? We're gonna talk about all that and so much more in part 2. So stay tuned, y'all, and remember that like dissolves like and opposites attract. Bye! Nom 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 nom. Gorgonzola cheese.